Hello, welcome back. Wherever you are tonight, and I hope, wherever it is, that it has some quality of stillness to it, some sense that the day has finally let go of you, I'm glad you're here. Maybe it's the bedroom, the one you know without needing the lights on, where you could navigate to the light switch or the water glass with your eyes closed and never miss. Maybe it's somewhere unfamiliar tonight, a couch that isn't quite yours, a room whose corners you haven't yet memorized. Maybe you're moving, the gentle rock of a train carrying you somewhere while your body has already decided to rest. Wherever it is, you've arrived. And arriving is enough. Go ahead and settle in. Actually settle. Not the version of settling that's secretly still waiting for something, but the complete kind. The kind that lets your weight become fully real against whatever is holding it. Let your shoulders drop from wherever they've been carrying the day. Let your breathing find its own slower rhythm, the one that doesn't need to be managed or watched, just allowed. You don't need to remember anything tonight. Nothing here is a test, and nothing needs to be retrieved tomorrow at speed. Some ideas will settle into you the way a colour settles into fabric left out in the sun too long, slowly, permanently, without anyone doing anything except leaving it there. Others will simply pass through, and that is completely fine. If you're new to this place, welcome. This is Late Space, and what we do here is take enormous, ancient, almost unthinkably large ideas and hold them at the pace of a long, unhurried evening. If you find that you'd like to return here on other nights like this one, a gentle like or subscribe helps other people who need somewhere quiet find their way here too. But that's for later, when you're more awake. Right now, there's only this. Tonight we are going to ask a question that sounds almost too large to hold, and that's precisely why we're going to hold it slowly, in small pieces, across a long time, the way you might carry water in cupped hands across a great distance, not all at once, but steadily. Trusting that most of it will make it to where it's going. What will the Earth look like in 10 trillion years? Not 10,000 years. Not 10 million. 10 trillion. A number so far beyond the ordinary scope of human thought that it requires, before we even begin, a kind of quiet recalibration of what long means. We are going to walk that path together tonight, through the death of our own star, through the merging of galaxies, through the slow extinguishing of starlight itself, all the way to a horizon so distant that the universe as we know it will have become something else entirely. And somewhere in that walk, we're going to keep returning to a very small, very specific question. What happens in each stage to this particular planet? This exact one. The one you're lying on right now, with its oceans and its air and its long green and blue history. Not the universe in the abstract. Earth, our Earth, followed as far into the future as physics will let us follow it. This is not a frightening story, though it touches endings, because at these scales, the concept of an ending becomes strange and unfamiliar in ways I think you'll find are actually rather beautiful. There is no urgency in any of this. Nothing here requires anything of you except your attention, offered gently, at whatever pace your eyes want to close. Let's begin. Close your eyes when you want to. We have all the time in the world tonight, which as it turns out is a phrase whose true scale we are only about to discover. Before we can talk about Earth in 10 trillion years, we need to build, patiently, a sense of what 10 trillion years actually is. Because our intuitions, however good they are for ordinary life, simply were not built for numbers like this, and without some scaffolding, the number will just slide past us as noise rather than settling in as something felt. Let's start close to home. 100 years is a long human life, stretched to its most generous limit. A person born at the start of one century, dying near the start of the next, having watched an entire epoch of technology and culture and history unfold and pass. 100 years feels, to us, like a very long time. It is the outer edge of what a single human awareness can personally witness. 1,000 years ago, the world looked entirely different. no printing press, no telescopes. Entire civilizations existed and dissolved that left barely a trace in what would eventually become recorded history. 1,000 years is already beyond the reach of anyone's direct memory, something we can only access through the layered, imperfect testimony of writing and archaeology. 1,000,000 years ago, our own species did not yet exist in its modern form. Early hominins were walking upright across the African savanna, using simple stone tools, their brains not yet capable of the language and abstraction that would eventually let their distant descendants build spacecraft and telescopes and, eventually, sit in quiet rooms at night listening to a voice describe the future of the universe. 1,000,000,000 years ago, Earth's atmosphere was still being fundamentally reshaped by the slow work of early photosynthetic life. The oxygen that now fills your lungs was, 1,000,000,000 years ago, still accumulating, poisoning the anaerobic life that had dominated the planet before, setting the stage for everything complex and oxygen-breathing that would eventually follow, including you. Now 1,000,000,000,000 years, that is 1,000 billions. If 1,000,000,000 years takes us back to a planet still learning to breathe oxygen, 1,000,000,000,000 years takes us into territory that has no analogue anywhere in Earth's actual history, because Earth itself is only about 4.5 billion years old. 1,000,000,000,000 years is more than 200 times older than the Earth itself. And we're not asking about 1,000,000,000,000 years tonight. We're asking about 10 trillion. 10 trillion years is roughly 725 times the current age of the universe. If you imagine the entire 13.8 billion year history of the cosmos, every galaxy that has ever formed, every star that has ever burned, the Big Bang itself, the first atoms, the first stars, the formation of the Milky Way, the formation of the Sun, the entire span of life on Earth, from the first microbe to this very moment, all of that compressed into a single day, then 10 trillion years would be a span of roughly 2 years stretched out from that one day. Everything we have ever known, as a species, as a planet, as a solar system, fits into less than a day. And we are asking what happens across 2 years measured on that same scale. This is the scale of tonight's question. Let it settle. There's no rush. Wherever you are, I hope you're comfortable. Let's take a slow breath together before we start moving forward in time. Because once we begin, we're going to be moving through eras that most human minds have never had reason to visit. And it helps to feel grounded before the ground itself, so to speak, starts to change. Let's begin with the part of this story that is the most familiar, the part that scientists have studied with the greatest confidence, because it involves nothing stranger than the well-understood physics of how stars like our Sun age and die. Our Sun, right now, tonight, is a middle-aged star. It is about 4.6 billion years old, and it has perhaps another 5 billion years remaining in its current stable hydrogen-burning phase, what astronomers call the main sequence. For that entire span, the Sun fuses hydrogen into helium in its core, releasing the steady stream of energy that has, for the entirety of Earth's biological history, made life here possible. But the Sun is not static even now. It is very gradually, almost imperceptibly, growing brighter. This happens because as hydrogen is converted to helium in the core becomes slightly denser and hotter, which increases the rate of fusion, which increases the Sun's overall luminosity. Over the course of 1 billion years, this brightening is significant enough to matter enormously for Earth's climate. In roughly 1 billion years from now, a comparatively near date, on the scale of tonight's conversation, the Sun will be bright enough that Earth's oceans begin an irreversible process of evaporation. The added water vapour in the atmosphere, itself a powerful greenhouse gas, accelerates the warming further in a self-reinforcing cycle. Eventually, the oceans boil away entirely. The surface becomes a scorched, waterless world. Whatever life remains, if any, would need to have found some other strategy entirely, deep underground perhaps, in pockets of moisture protected from the surface, though even this refuge would only last so long. This alone tells us something important. Earth's story as a living water-bearing planet is much shorter than Earth's story as a physical object. The Earth we know, blue, green, breathing, has perhaps 1 billion years left. The Earth as a rock, as a body orbiting a star, has considerably longer. About 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core entirely. It will then begin the dramatic final act of its stellar life. It will swell into what astronomers call a red giant. The outer layers of the Sun will expand outward, not gently, but enormously, potentially reaching as far as the current orbit of Earth, or very close to it. Whether Earth is actually engulfed by this expanding envelope of stellar material, or merely scorched from an agonizingly close distance as its orbit is disturbed by the Sun's changing mass, remains a subject of careful scientific debate. Some calculations suggest Earth might be pushed slightly outward as the Sun loses mass, escaping direct engulfment by a narrow margin. Others suggest the drag of moving through the Sun's expanded outer atmosphere would slow Earth's orbital motion enough to pull it inward and down, into the fire. Either way, the specific planet you're lying on right now, this rock, with its continents and its ocean basins and its long layered geological history, either becomes vapor, consumed directly into the body of the dying Sun, or becomes a bare, blackened, sterilized cinder closer to the swollen red giant than it has ever been, its surface reduced to something closer to molten rock than to the world we know. This happens on a timescale of about 5 billion years, which means that by the time we reach even 1 trillion years, let alone 10 trillion, this question of whether Earth survives as a physical object has already, long since, been settled. One way or another. Let me say something gently here, because I think it matters. This is not a story about our failure, or the universe's cruelty, or anything requiring grief in the way we usually understand grief. The Sun living and dying according to the physics of stellar evolution is not a tragedy. It's the same physical process that 5 billion years ago first assembled this Sun and this Earth out of a collapsing cloud of gas and dust. The Sun's death completes a cycle that has been running since long before Earth existed, and that cycle, stars forming, burning, dying, scattering their material back into space to be recycled into new stars and new planets, is one of the most fundamental, most beautiful processes in the entire universe. You are, right now, made of the recycled material of stars that lived and died long before the Sun ever formed. The carbon in your body, the oxygen you're breathing, the calcium in your bones, these were forged in the nuclear furnaces of earlier generations of stars. Stars that lived their lives and ended them in ways that scattered these elements across space, where they eventually became part of the cloud that formed our solar system. The Sun's eventual death, and Earth's eventual end, is simply this same process continuing forward, not an ending in the sense of a stopping, but a transformation, matter-changing form, energy being released, the ingredients for whatever comes next being scattered back into the vast reservoir of the galaxy. Knowing this doesn't erase the strangeness of the fact that our particular home, this particular rock we've spent our entire species' history on, will not last forever in its current form. But it reframes it, I think, from an ending into a passage, one stage in a story that continues. And tonight, we're going to follow that story much, much further than 5 billion years. Because even after the Sun is gone, even after Earth itself, in whatever form it survives, if it survives at all, has ceased to be a living world, the story does not stop. The universe keeps going, and there is something worth understanding in following it as far as we can. Let's talk about what happens if Earth, against the odds, somehow avoids direct destruction by the dying Sun's expansion, perhaps nudged just far enough outward by the loss of solar mass, perhaps surviving as a scorched, dead but structurally intact planet, orbiting what remains of its parent star. That remnant is called a white dwarf. After the Sun sheds its outer layers as a red giant, puffing them gently outward into space, forming what's called a planetary nebula, one of the most visually stunning objects in astronomy, glowing shells of gas lit by the exposed stellar core at their centre. What's left behind is an extraordinarily dense, hot ember, the Sun's original core, now stripped of its outer layers. Roughly the size of Earth, but containing something close to half the Sun's original mass. This white dwarf will not undergo any further nuclear fusion. It has no fuel left to burn. It simply radiates away its residual heat, slowly, over an almost incomprehensibly long span of time, cooling gradually from white-hot to a dim red ember to, eventually, something colder still. If Earth survives as an intact orbiting body around this white dwarf remnant, it would circle a dead star. No sunrise in any meaningful sense, the white dwarf would still glow, faintly, for a very long time, but with a fraction of the light and warmth the sun once provided. A permanent, deep twilight. No oceans, because those boiled away long before this point. No atmosphere worth the name, most likely, because whatever gases remained would have been stripped away or frozen solid onto the surface during the earlier, more violent phases of the sun's death. A cold, dark, airless rock circling a fading ember in a solar system that no longer resembles, in any meaningful way, the solar system you were born into. This configuration, Earth, or whatever remains of it, orbiting the white dwarf sun, could, in principle, remain relatively stable for an extremely long time. White dwarfs cool slowly. Over the course of many billions of years, the white dwarf that was once our sun would continue to dim, moving through the spectrum from white to yellow to orange, to a deep, faint red, and eventually towards something so cool and dim it would barely register as a source of light at all. This slow fade would take far longer than the current age of the universe. Estimates suggest that a white dwarf takes on the order of a quadrillion years, 1,000 trillion, to cool all the way down to the background temperature of the universe around it, becoming what physicists call a black dwarf, a cold, dark, inert sphere of degenerate matter, no longer glowing at all, effectively invisible except by its gravity. No black dwarfs currently exist anywhere in the universe, not one. The universe, at 13.8 billion years old, simply has not existed long enough for even the earliest white dwarfs to have cooled that far. This tells you something important about the scale we're discussing tonight. Even our own sun's white dwarf remnant will not have become a true black dwarf by the time we reach 10 trillion years. It will have cooled considerably, from its initial blazing white-hot temperature down to something much dimmer and redder, but it will still, technically, be glowing faintly in the deep infrared, a lingering ember from a star that stopped fusing hydrogen billions of years earlier. So, if Earth survives, in 10 trillion years it orbits this dim, barely glowing ember. A world in permanent, profound cold. No day and night in any meaningful sense, because there is no bright disk to rise and set. Only a faint red smudge on the horizon, growing dimmer, generation after unfathomably long generation of cosmic time, as the white dwarf continues its extraordinarily slow fade toward true darkness. But there's another consideration that changes this picture substantially, and it involves something other than the sun's own evolution, the gravitational influence of neighbouring stars over very long timescales. Even in the relatively calm environment of the outer solar system, over spans of billions of years, the accumulated gravitational tugs from passing stars, other stars in the galaxy that occasionally drift close enough, even at a distance of many light years, to exert a small but real gravitational influence, add up. This process is called dynamical relaxation, and it slowly perturbs the orbits of planets, injecting small amounts of chaos into what would otherwise be a stable clockwork system. Researchers studying the very long-term fate of our solar system have found that on a timescale of somewhere between 10 and 30 billion years, a star will likely pass close enough to trigger genuine dynamical instability among whatever planets remain in our solar system by that point. This instability would lead to what astronomers call strong planet-planet scattering, essentially. The remaining planets gravitationally jostling each other into increasingly erratic orbits, a slow-motion chaos that eventually resolves, in most simulated outcomes, with the ejection of nearly all the planets from the solar system entirely. Jupiter, by far the most massive planet, tends to survive these simulations. It's simply too large and too gravitationally dominant to be easily flung away. But smaller planets, and Earth, or whatever remnant of Earth remains at that point, orbiting the White Dwarf, would certainly qualify as small compared to Jupiter, are far more vulnerable. This means that somewhere in the span between 10 and 30 billion years from now, long before we reach even 1 trillion years, Earth's remnant, if it has survived the Sun's red giant phase at all, faces a real possibility of being gravitationally ejected from the solar system entirely. Flung out of orbit around its dead parent star, sent drifting alone into the vast cold spaces between stars, no longer a planet of any star at all, but what astronomers call a rogue planet, or an interstellar wanderer. If this happens, and the physics suggests it's a fairly likely outcome, not a rare exception, then by the time we reach 10 trillion years, Earth is not necessarily even in the same neighbourhood as its original solar system anymore. It is somewhere else entirely, drifting through the vast dark spaces of whatever the Milky Way has become by then, unattached to any star, its own internal heat. Whatever faint warmth remains from its formation, and from the slow decay of radioactive elements in its interior, the only source of energy it has left. A cold, dark, drifting rock, alone in the dark between the stars. This is one of the genuinely plausible fates for Earth by the time we reach the scale of 10 trillion years, not destroyed, not vaporized, but exiled, cast out from the only star it has ever known, wandering the galaxy in permanent, profound solitude. Wherever you are, I hope you're still comfortable. Let's pause here and breathe together for a moment. This is a lot to sit with, and there's no need to rush past it. I want you to notice something, if you can, about the emotional texture of what we've just described. It is strange and vast, and yes, there is something in it that might feel lonely. Earth, cast adrift, alone in the dark, no longer orbiting anything. But I want to offer you a different way of feeling this, if it's useful. Because Earth in this imagined future would not be unique in its solitude. It would be joining an enormous, almost uncountable population. Current estimates from planetary science suggest that rogue planets, planets that have been ejected from their original star systems and now drift freely through the galaxy, may actually outnumber the planets still orbiting stars. Some estimates suggest there could be trillions of rogue planets in the Milky Way alone, the accumulated debris of billions of years of planetary systems being gravitationally disrupted, merged and scattered. If Earth eventually joins this population, it does not join it alone in any true sense. It joins an entire cosmic community of wandering worlds, former members of other solar systems, orbiting other stars that have long since died or scattered their planets in turn. All of them now drifting silently through the vast dark, carrying with them whatever geological and chemical history they accumulated during their time as proper planets orbiting a proper star. There's something in that image I find quietly moving. Not a lonely fate, precisely, but a shared one. Every planetary system in the galaxy, given enough time, faces some version of this same slow scattering. Earth's eventual solitude, if it happens, would be one instance of an almost universal pattern, the natural long-term outcome of gravity working patiently on every star system that has ever formed. We are not being singled out. We are simply, eventually, joining everyone else. Let's widen our view now, because Earth's fate is entangled with something much larger, the fate of the entire galaxy it calls home. The Milky Way, right now, tonight, is approaching a collision, not an imminent one by human standards, but one that is already underway in the sense that the two galaxies involved are already moving toward each other, their mutual gravity slowly, inexorably drawing them together. The Andromeda Galaxy, our nearest large galactic neighbour, currently about 2.5 million light-years away, visible to the naked eye on a sufficiently dark night as a faint smudge of light in the northern sky, is approaching the Milky Way at roughly 110 kilometers per second. In about 4 billion years, give or take, the two galaxies will begin to merge. This merger, as we've discussed before in this series, is not a violent collision in the way two solid objects colliding would be. Galaxies are, on the scale of their individual stars, almost entirely empty space. The distances between stars within a galaxy are so vast, relative to the size of the stars themselves, that when two galaxies interpenetrate, the actual probability of any two individual stars colliding is close to zero. It's less like two crowds of people colliding and more like two very sparse swarms of fireflies passing gently through one another, each firefly continuing more or less along its own path, occasionally nudged by the gravitational tug of a nearby light. What does happen, over the course of this merger, a process that unfolds across hundreds of millions of years rather than in any dramatic instant, is gravitational reshuffling. Long streams of stars get flung outward into elegant sweeping tidal tails. Entire orbital configurations get rearranged. Some stars and any planets orbiting them get pulled toward the center of the newly merging system. Others get flung outward, away from the combined mass, into the outer, sparser reaches of what will eventually become a single, merged galaxy. Simulations run by NASA researchers studying this merger give roughly even odds, somewhere in the range of a coin flip, that our solar system, wherever it happens to be located by that point in cosmic history, gets pushed significantly farther from the galactic center than it currently sits. There's also a meaningful chance, somewhere around 1 in 8, according to some of these models, that our solar system is ejected from the galaxy entirely, cast out into the vast, empty intergalactic space between what remains of the Milky Way and Andromeda's other galactic neighbours. By the time this merger completes, a process that takes perhaps 2 to 3 billion years to fully settle into its final configuration, the two spiral galaxies we know today, with their elegant, organised arms, will have dissolved into something new. Astronomers have given this future merged galaxy an informal name, Milkomeda. Not a spiral anymore in all likelihood, but an elliptical galaxy, a more rounded, less organised, less structurally elegant shape. The graceful pinwheel arms of both original galaxies having been scrambled and redistributed by the chaos of their mutual gravitational embrace. If Earth's remnant, or the drifting, sunless rock it may have become by then, is still gravitationally bound to this newly merged galaxy at all, it exists somewhere within Milkomeda's new structure. If it was one of the objects ejected during the merger's gravitational chaos, it drifts instead through the vast, empty intergalactic space beyond, no longer part of any galaxy whatsoever. Either way, by roughly 7 billion years from now, still an almost trivially early point on the 10 trillion year scale we're exploring tonight, the Milky Way as a distinct, recognizable galaxy will no longer exist. And Earth's remnant, whatever form it has taken, exists somewhere within, or beyond, this newly formed cosmic structure. Now let's talk about light, specifically about what remains to illuminate this future landscape. Because as we move deeper into cosmic time, this question becomes increasingly central to understanding what any observer, hypothetical or otherwise, would actually see. Our current era of the universe's history is called, by cosmologists, the stelliferous era, literally, the star-filled era. It's the period during which the dominant source of energy generation across the cosmos comes from nuclear fusion inside stars, the birth, life, and eventual death of stellar objects, over and over, across billions of galaxies. We are right now roughly at the midpoint of this era, in terms of when it began and when it's expected to end, though midpoint undersells how early we actually are. Because the stelliferous era, by most calculations, extends from around 1 million years after the Big Bang, all the way out to somewhere between 100 trillion and 1,000 trillion years. Our current moment, 13 to 8 billion years into cosmic history, sits at a point that is, on a logarithmic scale of cosmic time, genuinely still quite close to the very beginning of this vast era. 10 trillion years puts us well within the later stages of the stelliferous era, but crucially, not past its end. Stars are still forming, still burning, still providing light, though the character of that light and the character of star formation itself will have changed enormously by this point. Here's why. Star formation requires fresh gas, specifically cold molecular hydrogen gas that can gravitationally collapse into new stars. But every generation of stars, as it forms and eventually dies, consumes some of this gas and doesn't return all of it. Massive stars, when they explode as supernovae, do scatter much of their material back into the surrounding galaxy, available for future star formation. But some material is lost permanently, locked away inside stellar remnants like white dwarfs, neutron stars and black holes, or ejected entirely from the galaxy in energetic outflows. Over time then, the total reservoir of star-forming gas in any galaxy gradually depletes. Star formation rates, which were exceptionally high in the early universe, have already been declining for billions of years, and this decline continues inexorably into the deep future. Current models suggest that ordinary star formation, the collapse of molecular gas clouds into new stars. The process responsible for essentially all star formation happening in galaxies today is expected to effectively cease somewhere between 1 trillion and 10 trillion years from now, primarily due to the exhaustion of available star-forming gas, compounded by the ongoing complications of gas recycling and the slow infall of whatever gas remains into galactic disks. 10 trillion years, in other words, sits right at the edge of when conventional star formation is expected to wind down almost entirely. By this point, in the merged remnant of the Milky Way and Andromeda cooling and aging, new stars are being born only very rarely, if at all, from whatever scraps of gas remain. But this doesn't mean the sky goes dark immediately, because there is one crucial exception to the general trend of stars dying out: the smallest, faintest, most miserly stars in the entire universe. Red dwarfs. Let me tell you something remarkable about red dwarf stars, because they are, in a very real sense, the true protagonists of this entire deep future story. Red dwarfs are the smallest stars capable of sustaining hydrogen fusion, typically less than half the mass of our Sun, some of them barely a tenth of the Sun's mass, right at the boundary below which an object simply isn't massive enough to ignite fusion at all. They are, by a wide margin, the most common type of star in the universe. Something like 70 to 75% of all stars in the Milky Way are red dwarfs. Our own Sun, a more massive, brighter and shorter-lived yellow star, is actually something of an outlier in terms of stellar demographics. Most stars are smaller, dimmer and far, far longer-lived than the Sun. The physicist Gregory Laughlin, in research conducted alongside Fred Adams and published in the influential paper that helped establish this entire framework of cosmological eras, described red dwarfs memorably. Red dwarfs are real misers at burning hydrogen. They hoard their energy, and some will still be around 10 trillion years from now, when the last sun-like star has long since exhausted its fuel supply and collapsed into a white dwarf. This is the key insight. Because red dwarfs burn their hydrogen fuel so slowly and so efficiently, a consequence of their lower core temperatures and pressures compared to more massive stars, their main sequence lifetimes stretch out to lengths that dwarf, almost unimaginably, the current age of the universe itself. The smallest, coolest red dwarfs are predicted to burn steadily for as long as 10 trillion years before finally exhausting their fuel. 10 trillion years. The exact figure we're asking about tonight, for Earth's fate, turns out to be almost precisely the lifetime of the very longest lived stars in the universe. This means that at 10 trillion years from now, the universe, and specifically whatever remains of Milky, is not yet completely dark. It is dominated almost entirely by these ancient, dim, red embers of stars, some of which are only now, at this unfathomably distant point in cosmic history, finally reaching the ends of their own extraordinarily patient lives. The sky in this era would not be filled with the bright, varied, colourful starlight we're accustomed to. It would be a sky of faint, uniform, deep red light, countless small stars glowing dimly, the last true stellar furnaces remaining anywhere in the observable universe, most of them older by that point than our current universe has ever been, in its entire history up to now. If Earth's remnant somehow still orbits a star at this point, perhaps not its original sun, which by 10 trillion years has long since faded into a cold, nearly invisible white dwarf, but perhaps captured, however improbably, into orbit around one of these ancient still-burning red dwarfs during the chaos of the galactic merger. The sky above it would be lit by this strange, deep, patient red glow. Not the warm yellow-white light of our current daytime sky. A deeper, dimmer, more muted illumination, the colour of embers rather than flame. Wherever you are, I hope you're still comfortable. There's a lot of strangeness in this future, and it's worth taking it slowly, letting each piece settle before we move to the next. I want to tell you something interesting that emerged from detailed computer modelling of how the smallest red dwarfs actually age, because it complicates the simple picture of stars just gradually fading and reveals something stranger and more specific. Research using sophisticated stellar evolution models has found that the very smallest, longest-lived red dwarfs, rather than simply dimming gradually as they age, the way we might naively expect, actually do something surprising near the very end of their extraordinarily long lives. As they finally begin to run low on the hydrogen fuel in their cores, rather than expanding into red giants the way our sun eventually will, these smallest stars instead become hotter and more luminous. They transform, temporarily, into what astronomers have taken to calling blue dwarfs. Smaller stars that brighten and shift toward hotter, bluer colours in the final stretch of their main sequence lives, before eventually cooling down into white dwarfs themselves. This matters for understanding the deep future, because it means that even as individual stars complete their extraordinarily long lifespans and die, the overall population of stars remaining in Milkomeda doesn't necessarily fade in some smooth, gradual, easily predictable way. Instead, there's a strange kind of compensating effect. The very oldest, longest-lived stars actually brighten somewhat in their final act, offsetting, to some degree, the gradual loss of stars that have already died. Some models suggest that future galaxies, populated overwhelmingly by these aging red-turned blue dwarfs, might actually remain nearly as luminous, in aggregate as galaxies are today, for several 100 billion years, before the accumulated losses finally outpace this compensating brightening, and the long, final fade toward true darkness begins in earnest. There is something almost poignant in this detail, a kind of stellar defiance, as if these smallest, most patient stars, having burned so slowly and so carefully for trillions of years, vastly outliving every more massive, more impressive, more dramatically luminous star around them, save one last burst of brightness for the very end. A final flare of light before the long dark. Now, having built this picture of what remains in the sky, let's return specifically to Earth. Because I promised you at the start of tonight's conversation that we would keep coming back to this one particular, small planet, and I want to honour that promise fully. By the time we reach 10 trillion years, Earth's fate has almost certainly already been determined by the earlier events we've discussed. The Sun's red giant expansion around 5 billion years from now, and the subsequent gravitational scattering of the solar system sometime in the following 10 to 30 billion years. There are, broadly, a small number of possible outcomes for the specific physical object that was once our home, and it's worth sitting with each of them in turn. The first possibility, Earth was directly engulfed and vaporized during the Sun's red giant phase. In this outcome, there simply is no Earth, in any physical sense, by the time we reach 10 trillion years. The atoms that once made up this planet, its iron core, its silicate mantle, its ocean water, the calcium in every skeleton that has ever existed here, the carbon in every living thing, have been absorbed into the body of the dying Sun, mixed into its outer layers, and eventually, as the Sun sheds those layers into a planetary nebula, scattered back out into the surrounding galaxy as diffuse gas and dust. In 10 trillion years, in this scenario, Earth exists only as a widely dispersed cloud of atoms, drifting somewhere within or beyond Milkomeda, potentially incorporated eventually into some future generation of stars or planets, forming from recycled stellar material. Though by 10 trillion years, as we've discussed, new star formation has largely ceased, meaning these atoms would likely remain simply as diffuse interstellar or intergalactic gas, waiting, perhaps forever, for a star-forming event that may never come. The second possibility, Earth narrowly escapes direct engulfment, surviving as a scorched, dead but structurally intact rock, orbiting the cooling white dwarf remnant of the Sun. In this outcome, Earth persists, for a time, as a genuine planetary body, though utterly transformed from the world we know. No oceans, no atmosphere worth the name, a blackened, cratered, airless surface, orbiting an ember of a star. This configuration could last for a very long time, but as we discussed, the accumulated gravitational tugs of passing stars over 10 to 30 billion years make it likely, not certain, but likely, that Earth eventually gets gravitationally ejected from this orbit entirely. Which brings us to the third, and perhaps most probable, possibility by the time we reach 10 trillion years, Earth as a rogue planet. Ejected from its original solar system sometime in the tens of billions of years following the Sun's death, Earth, or what remains of it, drifts alone through the vast spaces of the galaxy, unattached to any star, its surface locked in permanent, profound cold. Its only warmth coming from whatever residual heat remains deep in its own interior, and from the extraordinarily faint, diffuse light of the ancient red dwarfs and merged galactic remnants it might occasionally, distantly pass. In this third scenario, which I find, honestly, the most likely outcome given everything we currently understand about long-term orbital dynamics, Earth at 10 trillion years is a solitary, frozen world, drifting through a universe that has become, in its own particular corner, dominated by the faint red glow of the last remaining stars, moving silently through space at whatever velocity it acquired during its ejection, following a trajectory determined by the last significant gravitational encounter it experienced, sometime in the deep past, tens of billions of years earlier. No sunrise, no sunset, no blue sky, because there is no atmosphere left to scatter light, and there is, in any case, no bright star nearby to provide the light in the first place. Just an endless, silent drift through the profound dark, occasionally illuminated, faintly, by the distant red glow of ancient stars still patiently burning somewhere far across the merged remains of what was once two separate, beautiful spiral galaxies. I want to pause here and offer you something, because I recognise that this picture, taken all at once, could feel bleak if you let it land that way. And I don't think bleakness is actually the most honest emotional response to what we've just described. I think there's something else available here, something worth reaching for. Consider what Earth actually is in this deep future scenario. A rogue planet, drifting alone through space, carries within itself an entire geological and chemical history that took over 4.5 billion years to accumulate. Even frozen, even dark, even utterly without atmosphere or ocean, this object would still contain, layered within its rock, the entire record of everything that ever happened here. The iron core that generated a protective magnetic field for billions of years, the tectonic plates that built and destroyed mountain ranges, opened and closed oceans over and over for most of the planet's existence. The fossilized remains, deep in sedimentary layers, of every form of life that ever emerged and eventually went extinct here, the trilobites, the dinosaurs, the countless species we'll never even know existed, and, somewhere in there, the traces, however faint, however eventually eroded by time, of us, of everything humanity ever built, everything we ever wrote down, everything we ever felt. None of that history disappears simply because the planet stops orbiting a star. The rock remains the rock. The layered record remains, physically, embedded in the material itself, even as it drifts through a cold and starless dark that no living thing will ever again witness. There is something in this that I find, at this hour, genuinely moving, rather than merely sad. Earth, even in its most desolate imaginable future, still carries forward, silently, unread by anyone, but physically real nonetheless. the entire accumulated story of everything that ever happened on its surface. A geological archive drifting alone through space, its pages never again to be turned, but existing nonetheless. Persisting, present, real, let's widen our view once more, because I want to make sure we understand not just Earth's specific fate, but the larger cosmic context surrounding it. Because I think that context actually changes how we feel about Earth's own particular story. By 10 trillion years from now, the universe itself has continued its relentless expansion. And this expansion has had a profound effect on what any hypothetical observer anywhere within Milkomeda would actually be able to see. We've discussed in earlier episodes how the accelerating expansion of the universe, driven by dark energy, is gradually carrying distant galaxies beyond our observable horizon, beyond the point where their light, even travelling at the maximum possible speed, could ever reach us again. This process, which has already begun and is already underway, right now, tonight, accelerates further as time goes on. By roughly 100 billion years from now, long before we reach even 1 trillion, let alone 10, every galaxy beyond our own local group will have been carried beyond the cosmic horizon. Any hypothetical astronomer living in Milkomeda at that point, or afterward looking out into the night sky with the most powerful conceivable telescope, would see nothing beyond the boundaries of their own merged galactic system. No other galaxies. No evidence from direct observation alone that other galaxies ever existed. The expanding universe will have carried the evidence of its own vastness permanently out of reach. By 10 trillion years, this isolation is total and ancient. Milkomeda, or whatever it has further evolved into by that point, having potentially absorbed a few additional small dwarf galaxies from the local group along the way, exists as an island. A single, isolated system of stars, aging and dimming, surrounded by an ocean of dark, empty space in every direction, with no other galaxies visible. No other lights on the horizon, nothing to suggest that the universe was ever anything other than this one solitary, slowly fading structure. Earth, wherever it is by this point, whether drifting freely as a rogue planet, or still, against the statistical odds, orbiting some ancient stellar remnant, exists within, or perhaps beyond, this isolated island, a small, cold, forgotten fragment of a much larger, equally isolated and equally forgotten cosmic structure. And yet the light from those ancient, patient red dwarfs, still burning after 10 trillion years, is real light. Actual photons, actual energy, actual illumination, however faint, cast across the profound darkness of this isolated future. The universe, even at this stage, even having lost the vast majority of the vivid, varied brightness that characterizes our current cosmic era, has not gone entirely dark. Not yet. There is still light. There are still, somewhere, the faint, dim embers of the very last stars, doing what stars do, which is simply continuing to burn, for as long as their fuel allows, indifferent to whether anyone is left to witness it. Wherever you are, I hope you're comfortable. We've travelled a very long way tonight, and there's more still ahead, but let's rest here for a moment in this strange, quiet, red-lit future before we continue further. I want to tell you something about what a hypothetical observer, not a human, almost certainly not anything we would recognise as biological life in any conventional sense, but simply as a thought experiment, might actually perceive, standing on a surviving rocky world somewhere within Milkomeda at the 10 trillion year mark. The sky above would be dominated by the faint, deep red glow of the last remaining red dwarf stars, not the bright, varied, twinkling multitude we see tonight, but a much sparser scattering of dim embers, most of the stars that once populated this merged galaxy's spiral arms having already faded entirely into invisible white dwarfs. Then further still toward the eventual, extraordinarily slow cooling that leads to true, permanent darkness. There would be no Milky Way band arching overhead the way we see it tonight. That beautiful, hazy river of light created by the combined glow of billions of individual stars in our galaxy's disk, viewed edge-on. That particular visual structure depends on the specific spiral shape of our current galaxy, a shape that will have long since dissolved into the more diffuse, elliptical structure of Milkomeda, its stars redistributed by the ancient merger into a rounder, less organized configuration. There would be no other galaxies visible at all. Andromeda long since merged and absorbed every other galaxy in the observable universe, carried permanently beyond the cosmic horizon by the relentless work of accelerating expansion. The temperature of empty space itself, the cosmic microwave background. That ancient afterglow of the Big Bang, which currently sits at a chilly 2.7 degrees above absolute zero, would have cooled further still, the relentless expansion of the universe having stretched this ancient radiation to even longer, even fainter wavelengths, making the background temperature of the universe itself colder than it has ever been in its entire history up to this point. And somewhere within this vast, cold, mostly dark, sparsely red-lit expanse would be Earth. Or what remains of it. A small, quiet fragment of a story that began 4.5 billion years earlier in the same collapsing cloud of gas and dust that formed the now long-dead sun. I want to shift now towards something a little different. A question about what any form of intelligence, any form of awareness might actually be doing if it somehow still existed at this unfathomably distant point in cosmic history. Because this question, though deeply speculative, connects to something the physicist Freeman Dyson proposed decades ago, and that I find genuinely beautiful to sit with, even in its uncertainty. Dyson, writing in 1979, considered the question of whether intelligence, consciousness, awareness, the capacity to think and to experience, could, in principle, persist indefinitely into the deep future of an expanding, cooling universe. His proposal, refined and built upon by later researchers including Fred Adams and Gregory Laughlin in their work on the long-term fate of the universe, rested on an elegant idea that the rate of metabolism, and therefore perhaps the rate of subjective experience or consciousness, might not need to remain fixed as the universe cools. A sufficiently patient and adaptable form of intelligence, Dyson suggested, might be able to slow its own internal processes to match the ever-decreasing energy available in an aging universe, thinking more slowly, but thinking nonetheless, stretching each thought, each moment of awareness, across a proportionally longer span of external time, so that subjectively, from the inside, the experience of time passing might feel continuous and unbroken, even as the external universe grows colder and darker around it. This is, I want to be clear, deeply speculative. Modern physics has identified real energy constraints on computation and on any physical process that might constitute thought, constraints that Dyson's original 1979 paper did not fully anticipate, and the picture that has emerged from more recent analysis is considerably less optimistic than his original proposal. Whether any form of information processing, any form of awareness, could genuinely persist across trillion-year timescales, adapting to ever-decreasing energy availability, remains a profoundly open and uncertain question. But I find the spirit of the idea worth holding on to, gently at this hour. Not as a confirmed prediction, but as a kind of permission to imagine that awareness, in some form, somewhere, might find a way to continue witnessing the universe's long, slow story, even as that story moves into territory as strange and cold and quiet as the one we're describing tonight. If nothing does, if awareness, consciousness, the capacity to notice and to wonder, is something that exists only briefly, only in this particular early era of cosmic history, only in this particular narrow window when stars are bright and planets are warm and oceans are liquid, then that fact makes this moment, right now, the one you're currently living through, extraordinarily precious. Not because it lasts forever, because it doesn't, and yet it's happening anyway, right now, in you, in this room, in this specific configuration of matter that has organized itself, however briefly, into something capable of understanding its own cosmic context. Let's return one more time to Earth specifically, because I want to make sure we've given this small particular planet its full and proper attention before we bring tonight's journey to its close. 10 trillion years from now, in the most statistically likely scenario given everything current science understands about long-term orbital dynamics, Earth exists as a rogue planet, a cold, dark, frozen world, drifting alone through the vast, sparsely red-lit expanse of Milkomeda, or perhaps having been flung entirely beyond even that merged galaxy's boundaries, drifting instead through the profound emptiness of intergalactic space. Its surface, whatever remains of it, would be locked in permanent, absolute cold, colder than anywhere on Earth has ever been in its entire geological history, colder than the deepest Antarctic winter, colder than anywhere life as we understand it could possibly persist. Any water that once existed on its surface would have long since either boiled away during the sun's earlier red giant phase, or, if somehow preserved past that point, would now exist only as solid ice, locked permanently in place, with no source of heat remaining anywhere nearby to ever melt it again. Its interior, however, might still retain some faint warmth. Earth's core, even today, remains extraordinarily hot, heated partly by residual heat from the planet's original formation and partly by the ongoing radioactive decay of elements like uranium and thorium deep within the mantle. This internal heat source, while it does gradually diminish over time, does so on a timescale of many billions of years, meaning that even after 10 trillion years it's plausible, though not certain, that Earth's deep interior retains some residual warmth, some faint geological activity, even as its surface remains locked in absolute, starlit or starless cold. In this sense, Earth, 10 trillion years from now, would be a study in profound contrast. A frozen, dead, lightless surface drifting silently through space, and beneath that surface, in the planet's deep interior, perhaps still some faint trace of the same geological heat that billions of years earlier drove plate tectonics, built mountain ranges, and created the conditions that eventually allowed life to emerge and flourish here in the first place. A cold shell around a fading ember, silent on the outside, and perhaps deep within, still very faintly warm. Wherever you are, I hope you're comfortable. We're nearing the end of tonight's long journey, and I want to bring us back gently to a wider and perhaps more comforting perspective before we close. Because everything we've described tonight, the death of the sun, the merger of galaxies, the slow fade of starlight, Earth's possible ejection into the cold dark of intergalactic space, all of this describes a genuine scientifically grounded projection of what current physics suggests is likely to happen, given enough time. And it is, undeniably, a picture that involves loss. The Earth we know, with its oceans and its forests and its cities and its entire biological and cultural history, does not last 10 trillion years. It doesn't even last 1 billion years, in any form we would recognize as home. But I want to offer you something to hold alongside that fact, something that I think is equally true and equally important. 10 trillion years is such an extraordinarily long span of time that almost nothing about the present moment, nothing about you, about your particular concerns tonight, about the specific shape of your life and your loves and your worries, has any meaningful relationship to what happens at that distant point in cosmic history. And this is not a diminishment. It's a liberation, if you let it be one. You do not need to carry the weight of 10 trillion years on your shoulders tonight. That timescale belongs to physics, to cosmology, to the patient, indifferent unfolding of natural law across a span of time so vast it makes the entire history of human civilization look like a single, barely measurable instant. It does not belong to you, personally, in any way that should add weight to your evening. What belongs to you, right now, is this moment, this room, this breath, the oceans that still exist, right now, full and blue and teeming with life, exactly as they have been for the entire span of your life and the lives of everyone you have ever known. The sun that still rises tomorrow morning, warm and bright and utterly reliable, exactly as it has risen every morning for your entire life and for the entire history of your species. 10 trillion years from now, all of that is gone, transformed into something else entirely. But right now, tonight, none of it is gone. It's all still here. The Earth beneath you, or beneath whatever surface you're resting on, is still turning gently, still orbiting a young, stable, healthy star, still carrying its oceans and its forests and its cities and its long. Extraordinary biological history forward. One more day, one more night, one more quiet hour like this one. I want to leave you with one final image before we close, because I think it captures something important about how to hold everything we've discussed tonight. Imagine, if you can, a vast river, one that begins somewhere in high mountains and eventually, after an extraordinarily long journey, reaches the sea. If you stood at the very beginning of that river, at its narrow mountain source, and tried to describe everything that would eventually happen to that water, the turns it would take, the landscapes it would carve, the eventual, inevitable moment when it dissolves into the vast, undifferentiated body of the ocean, you might feel, if you focused only on that final dissolution, a kind of sadness. The river, as a distinct thing, does not last forever. It becomes something else. It becomes part of something larger, and it stops being a river. But if you stood there, at the source, and simply watched the water flow, clear, cold, moving with purpose and energy down through the mountain valley, catching the light, supporting the fish and the plants and the small creatures that depend on it, you would see something that is, in its own present moment, complete, not diminished by its eventual dissolution into the sea. Simply, fully itself, right now, in this stretch of its journey. Earth tonight is like that river near its source, full, alive, carrying an extraordinary richness of water and air and life and light, moving through its particular stretch of cosmic time with its own complete present reality. That it will, eventually, over a span of time so vast it barely relates to human experience at all, transform into something else, a scorched ember, a frozen rogue world, drifting alone through a dark and mostly starless future, does not diminish what it is. Right now, tonight, you are part of that present richness. A conscious observer capable of understanding this entire cosmic story, lying somewhere warm and safe on a living, breathing planet, at a moment in cosmic history when stars are bright and oceans are full and the universe is, relatively speaking, still young. That is worth feeling good about. Genuinely, fully, without needing to erase or ignore everything else we've discussed tonight. Let's come all the way down now, slowly, gently, towards sleep. Here is what is true, as carefully and honestly as I can say it. In about 1 billion years, the sun's gradually increasing brightness will boil away Earth's oceans, ending the planet's long era as a water-bearing world. In about 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, likely engulfing Earth directly, or at the very least, scorching it into a lifeless cinder at a distance far closer than its current safe orbit. If Earth somehow survives this phase intact, it will orbit the cooling white dwarf remnant of the sun, a permanent, dim ember, for some further span of time, until, somewhere between 10 and 30 billion years from now, the accumulated gravitational influence of passing stars likely scatters the remaining solar system, quite possibly ejecting Earth entirely into the cold, dark space between the stars. Around the same broad era, 4 to 7 billion years from now, the Milky Way merges with the Andromeda Galaxy, dissolving both into a new elliptical structure that astronomers call Milkomeda, a merger during which our solar system, wherever it happens to be located, faces meaningful odds of being flung outward, or ejected from the galaxy entirely. By roughly 1 to 10 trillion years from now, ordinary star formation across this merged galaxy winds down almost completely as the available reservoir of star-forming gas is finally exhausted. What remains, still burning, are the smallest, most patient stars in the universe, red dwarfs, whose extraordinarily long, miserly lifespans allow some of them to persist in a stable, hydrogen-burning state for up to 10 trillion years, very nearly the exact span of time we've been asking about tonight. And Earth, by this point, 10 trillion years after its formation, most likely exists as a cold, dark, rogue planet, drifting alone through the sparsely red-lit expanse of this ancient, merged, isolated galaxy, its surface locked in permanent cold, its interior perhaps still holding some last, faint trace of the geological warmth that once made it home to oceans, and forests, and cities, and you. This is not a story to fear. It's a story to understand, gently, the way you might come to understand and accept the eventual end of any long and beautiful thing, while still, fully and completely, appreciating everything that thing is, right now, in this moment, before that ending ever arrives. Close your eyes if they're not already closed. You are here, tonight, on a young, warm, living world. The oceans are full. The sun, wherever it currently sits in the sky on the other side of the planet from you, is bright and stable and reliable, exactly as it has been for your entire life. The air you're breathing carries oxygen that plants and algae have been patiently producing for billions of years. The gravity holding you gently against whatever surface you're resting on is generated by a planet that has not yet begun any part of the long, slow transformation we've described tonight. None of what we discussed happens today. None of it happens this year, or this century, or within any span of time that has ever mattered to any human life that has ever been lived, or ever will be lived. What happens today, right now, is this. You rest. You let the weight of an impossibly long future settle into something quiet and manageable, the way a very large stone, dropped into very deep water, eventually settles gently onto a soft and forgiving floor. You remember, if you can, that 10 trillion years from now belongs to physics, and that tonight belongs to you. Thank you for spending this time here. Thank you for holding something this vast, this strange, this far beyond ordinary human scale, and doing it gently, without needing it resolved, without needing certainty, simply letting it be as large and as quiet as it actually is. Sleep well. The earth beneath you is turning, as it always has, toward another morning, and somewhere, 10 trillion years from now, in a future none of us will ever see. Something that was once this very planet may still be drifting, quietly, faithfully, through the dark, carrying forward, in its silent rock, the entire long story of everything that ever happened here. Good night.